10?
1 hour, 11 minutes.
Fair enough. Yeah, I think that'll be plenty of time. All right, guys, let's go ahead and get settled. My name is Jose Crisega, and I work at Johnson Conworthy Combustion. I'm a process engineer, and I really specialize in burner design and burner testing. Okay, and that's essentially what we're going to talk about today. We're going to spend really a little bit of time of practical, looking at the practical application of the actual burner testing. So it's a couple good things about that. There's only like one equation in the whole presentation, which is really good. And it's not even an equation, really. It's just a little bit of geometrical stuff. So it's not going to be complicated. So today is going to be a little bit easy on the eyes. I saw what Mark did on the last session with his fluid flow and CFD. So I figure we ease on since it is close to Monday anyways, right? And I actually came to school here. I did my undergrads and my master's here, but I did it in mechanical engineering. So I think most of you guys are chemical engineers. There's some Mickeys over there, I think. Awesome. And so you guys can probably take me to town on chemistry. But luckily we're not going to focus a whole lot on that just yet. So really what I want to get done today is I want you guys to understand really why do we do burner testing? What is the reason behind it? Why is it useful, and why is it sought after in the industry? And then finally just get a little bit of understanding about NOx corrections there at the end. So can anyone just wild guess, why do we do tests on burners? What was that again?
Models aren't 100% reliable.
Okay, so models aren't 100% reliable. Okay. Any other wild guess? Is there anything that you guys do have you guys ever tested anything? Has anybody gone test drive a car, for example? Right? So testing is actually something that we do a lot. When we go get a phone, when we go really make any commitment that it's pretty long, whether it's phone, computer, we typically go out there and try it out just to see what it does, how far can it go, what can it do. And really a burner test is just that. Okay, it's the ability that we have to show to ourselves, show to our customers, that we are first meeting all the applicable guarantees that were set forth at the beginning of the project. So that's the first thing that we look for. Okay, are we meeting all the contractual guarantees that we set forth at the beginning, whether it's emissions, whether it is pressure drop across the burner, heat capacity. There are a couple things in there that you look at when you do a burner test. And so that's the first thing we look at. The next thing that we do is we try to record what are the limits, right? What happens when you push that burner outside the operating envelope? Really, a burner test will be the safest spot to do that because you're in a testing facility and it's only one burner. When you think about a heater, you can have hundreds of burners in one heater, and it's just not practical to do that, okay? The next one is to validate CFD. So early on we said, well, models aren't 100% accurate. So we utilize that physical testing to validate our CFD modeling so then it can be applied to a bigger scale. And finally, for R&D, for new technology, typically when you come up with a new burner model or when it's a new technology is going to be applied, no one is really going to go ahead and apply in a refinery they have to live with for like 30 years without even had any testing behind it. So in R&D developments or in new developments, it's the best way to bring out real life data to the customer, and it gives substance to our claims. So we're really going to cover burner testing in 3 quick sections, right? So we're going to talk about furnace selection and setup, how do we simulate the fuel, which is one of the things that you really want to get right when you're doing a burner test, and what is the test procedure, and how to really measure all the different parameters during the test. Before we get to choosing a furnace, first we need to understand what are we testing, right? So I don't know if you have had an opportunity to talk about the different burner models, but they come in very different ways and shapes, okay? They can be natural draft, forced draft, and we'll talk about what that is in a second, but the premix, dilution, there is a lot of different characteristics to burners. Even the application, like the final heater, where they're going to be in, it affects the way you test your burner. So it's really important to understand really what is the process that you're going to be supplying your burner to, hence the title process engineer, right? It's just understanding what is the end goal necessarily rather than knowing how the burners work is really what makes us better than other people out there. So once we have identified, the firing orientation or the type of burner, the type of fuel, the type of applications that is going to be used in the field, then we select a test furnace. Currently, I think we have about 10 test furnaces here in Tulsa, Oklahoma. There's a few others in another country. And so each of these furnaces are shaped a little bit differently. And what they're trying to do when these furnaces were designed for our test furnaces, they're sort of like a little slice of a full-scale furnace. And what we're looking to do is really take a slice of that final furnace and show that to the customer with typically a single burner test. Sometimes it can be up to 2, 3, 4, 6, depending on the test furnace that we're using. So one of the things that we looked at, firing orientation, if we are to boil it down, the first things that we looked at is the fire orientation, where you're firing from the floor up or from the roof down. Applications when burners can be installed in the wall of the heater and they're firing horizontally. And then we have terrace walls, which is essentially the orientation. So in there, the burners are a little bit tilted. Again, all of those are driven by the final heater design. And then finally, how is the oxidizer or the oxygen being delivered to the burner? Right? We all know in order to have combustion, you need essentially 3 things: fuel, air, or oxygen, really, and an ignition source. That's how you're going to get that combustion going. So depending on the heater design, you can have a natural draft burner. And what that means is that you're utilizing the buoyancy inside the heater to inspirate the air. So if you will, the hot airs inside the furnace are lighter than the air outside, therefore they're just going to float. And when they do that, then some air is going to be inspirated through an opening, and the opening will be on the burner. So that will be a natural draft type. There are some cases where that is not done. We have a forced draft, which is you have literally a fan, and this guy right here, we call him Big Blue because it's huge. I didn't get somebody, but I'm about this tall right next to it. So it's pretty big. And what it is just essentially very, very dry, that you can throttle the amount of air that you literally push through the burner. And Big Blue is actually equipped also with the ability to preheat the air. Some heaters utilize some of the heat from the exhaust, and they do a little bit of heat exchange and try to put that energy back into the heater. And they do that by preheating air. And finally, turbine exhaust gas is just literally what it sounds like. So some refineries use a turbine as the energy generator. And what they do is the exhaust from that gas typically comes out at a really high temperature, about 1,000 degrees F. And so they try to utilize that energy to put it into a heater, and that way they can gain a little bit more efficiency. So the bottom picture here is essentially the setup to simulate that turbine exhaust gas. And there's actually another application that's kind of neat. I mean, we have tested that before. It's called oxifier. So one of the big drivers on newer technology is lower emissions, lower NOx emissions specifically. And so an easy way to not have NOx is to just not have hydrogen. And so what they do is they literally pipe up oxygen, pure oxygen, through these burners, and then make the combustion that way. And if you don't have any nitrogen or any leakage, then you will have pretty close to zero NOx outside of the stack, which is pretty cool. So let's talk about how do we look at the decline of fuel simulation. So depending on where you are located in the country, you will have different fuel compositions, and even depending on the processes that you're running. A lot of refineries tend to use byproducts of their product to use as fuel, right? Sort of like they call it, sort of like free fuel, right? And so the one big part of our testing is making sure our burners are stable with that particular fuel. And there are a couple of things that we look at. One of them is we look at the hydrogen content. Hydrogen content is one of the first things that we're trying to match in our fuel composition, simply because hydrogen has a unique capability of burning really fast and burning really hot. So when it does that, it brings questions to regards of emissions, right? So that flame temperature is what we're looking to replicate, and really there is no other fuel that'll give you that same really fast flame. And then we look at the hydrogen with the hydrocarbons and inerts to get an idea of the adiabatic flame temperature. And adiabatic flame temperature is just a fancy word that help us understand the temperature at which that fuel is burning. It's not necessarily the actual flame temperature, but it's just sort of like a reference, just to give you a reference scale. Because the adiabatic flame temperature then gives us an idea of about the thermal NOx production that burner will have. Next thing we look at is the fuel-bound nitrogen. So does your fuel has a component such as ammonia, for example? When ammonia is present on your fuel and it goes through combustion, essentially you get a free radical there that will convert straight onto NOx. So that's really important to understand, because when you are providing a NOx guarantee, the amount of ammonia present in your fuel will definitely make a difference. And finally, we have the combustion air requirement, just how much air do you need to combust the heat release that you have, and that really comes with the burner design. So you size your burner accordingly. Typically, when you're doing a test, you are specify the burner, we call it burner pressure drop. And if you will, it's essentially the amount of energy, the amount of pressure that you need to get a given volume of air through a geometry. And finally, we use the heating value and the molecular weight of the fuel for gas tip sizing, because they also tell you what pressure you have available on site. Here, another thing that you look at on testing is obviously cost, right? So testing is actually sold to a customer, and so you have to work with a budget. And this right here gives us a brief idea of the cost of each of the fuels, okay? And you can see obviously the cheapest one for us here in Tulsa is going to be Tulsa Natural Gas, because it's really available at the tap there. But there are other things that you want to look at, in the sense of, look at hydrogen, for example. It's only 3 times the cost of natural gas. But if we take a second and look at the LHV, the heating value of hydrogen, it's actually 1/3 of natural gas. So by the time you do the math, if you figure out the amount of flow that you need to get the same heat release of hydrogen compared to natural gas, then hydrogen becomes about 10 times more expensive than natural gas. So if you think about it, sometimes when we go to lunch, we leave the burner running because we're just not going to take it down for going to lunch, right? It's about an hour there. So typically we switch to natural gas because in an hour you can spend, say, $100 just firing 10 million BTUs an hour. Well, if you did that with hydrogen, that would have been $1,000. So having little things like this in mind when you are building your test or when you are executing your test really come handy at the time of having a successful burner test. And in this table also we have the actual fuel composition we have available in our test facility. So there are many different hydrocarbons that a customer can come up with from their processes. What we typically tend to do is we boil it down to about 5 or 6 different components, and we blend those and then we test them. So that's essentially what we do. And so whenever we're thinking about that test fuel, the first thing we look at is we look at the customer fuel. We try to understand the adiabatic flame temperature of their fuel, the low heating value, molecular weight, Wolbe index, and a couple other different characteristics of that particular fuel. Once we do that, like we said a little bit ago, we try to match that hydrogen. And the reason we do that first is because it's really hard to get it around it. If you have a fuel that has a high presence of hydrogen, if you don't use hydrogen, you will not get to it. And I say that, and I'm going to say 99% of the time you won't get there. After we do that, when we also try to match the inerts. Inerts make a pretty big difference on that adiabatic flame temperature and the molecular weight. And then finally, sure, we look at the unsaturates and saturates, but more importantly, we use natural gas and propane to then match that heating value and molecular weight of that test fuel. So once you do those, then we look at now our fuel characteristics. We compare those with of the customers, and if they're close enough, then good, we got a test fuel. At this point, we actually do communicate that test fuel to the customer, and then there are a couple conversations about it, and then everybody agrees that's the best way to recreate that fuel or to simulate that fuel, and then we get out to the test pad. So let's look at what a test procedure will look like. So API 535, and API just stands for American Petroleum Institute. They actually came up with a procedure of a standard burner test, okay? And typically in that procedure, what you test is your design firing rate, a normal firing rate, and a minimum fire rate. So those are the things they ask for. They ask for to do an expected light off of the burner, and something that we call CO break. And what a CO break is, if you will imagine that you're operating your burner and it's in your furnace, and you can imagine as you introduce fuel, there's going to be a point in which you can no longer entrain any more air through the burner just because you are geometrically limited. Well, if you keep increasing the fuel, the excess oxygen inside the box is going to get close and close and close to zero. So CO break is the point when you got past that, because you're going to get to a point where you will not have enough air to combust the fuel that you're putting into the furnace, and now carbon monoxide will form, or uncombustibles will also form as well. So that's what they call a CO break. So the customer really wants to have an understanding at what point will you start forming CO. And that's actually used for things like fuel trip. So if you, in refineries, they typically have a monitor that looks at the fuel pressure, and once it goes past a certain threshold, then it will just essentially cut the fuel to that particular burner because something else is wrong. This is actually fixing to change on the next year. A couple other data points are going to be added in there. And I know it may seem a little bit trivial, the number of points. I think if you count them, they're probably going to be like 7 in there, 7 and 8 points. But then when you factor in whether the burner has more than one fuel, you have to do all of those for every single fuel. And then when you factor in whether you have natural draft and forced draft, then you have to do it for those cases. So, and then you have some customers that like to look at other things, such as, can we do CO break by air? And what that means is, can you close the burner opening until the burner literally runs out of air? So there's a lot of flavors to different testings, and those are typically, again, driven by the customer. I know what I'm looking for, and this typically covers it, and then the customer has their own requirements too. This is what a test data looks like. So if you were out to go to a furnace and you were going to take a data point, this is quite literally what you get. So there are a lot of numbers. There really are. So there's a lot of things to look at the same time, and there's a lot of things that you're measuring, so you can accurately describe that particular heater. Okay? So, and again, this is specifically to us. If you go elsewhere, I'm pretty sure the screen will look different. I don't know. One thing I like to bring this up is because I think about 25 years ago is whenever this was implemented in our facility. They had the ability to automatically record and capture data. Before that, they actually did it by hand. So there was actually the test engineer's job was to come out there with a notepad, I guess, and he would write down all these different values, and then he would go back inside and calculate what he had. You know, because some of these values are measurements and some of them are calculations. But then he will go back inside, check out his numbers, figure out if it was okay, and then move on to the next data point. So then figure doing that, say, 20 times in one day. Or if you have a test procedure that had 50 points, just imagine how long that would take to finish.
So what is custom fuel type? How many fuel type over here?
Fuel type, custom fuel type. Okay. So in this particular case, I have, the burners have, typically a burner will have only one fuel connection. But there are some applications when there is a byproduct that gets injected in the burner. Okay? So in this case, that's the pink you see, it says PSA. So that's pressure swim absorption. So this is probably I don't know, I'm pretty sure I did this test. This is a downfire reformer. And actually using turbine exhaust gas too. So it's a downfire reformer that you have a main fuel that is your RFG, that stands for refinery fuel gas, okay? And so you can see that the RFG is firing about 2.44 million BTUs an hour, and in addition to that, there's a PSA that is made out of hydrogen, total natural gas, and nitrogen, that is firing about 5.73 million BTUs an hour. So those are on the main burner. And then I have the TEG burner, the way we simulate it is actually we have a separate burner on the side. And the flue gas or the combustion products of that burner is what get fed to the main burner. And so I can tell that the TEG burner is firing about 8 million BTUs an hour. And it's providing a combustion temperature of about 963 degrees F. So in this particular case, I have 3 different fuel streams going to the 2 burners, and that's the way we monitor it then.
So that's very specific to like the clients individually.
Absolutely. This would be, and I would agree with you if you were to say this is more complicated than most test burners. Typically, most test burners are not that much in depth, but you still have about, I would say, 70% of the stuff that's showing up there. Okay. But that really brings up a good point, though, in the fuel line. So you guys see the upper part of your screen here, you have all the different fuel lines that I have available in that furnace. And so what I have my operator do is I have him open the valve to each. I can tailor-made which fuel, whether it's hydrogen, nitrogen, propane, which fuel goes to each of the lanes, and then I have him open the lane accordingly to a percentage to make a fuel blend that I design. And then that gets into a header or to a manifold, and then from that manifold then it gets fed to the individual burner. In this case also need that, so after you have that fuel blend, what happens is it goes to a heat exchanger, because this particular process happens to have fuel temperatures that were greater than ambient. So you can see that the PSA temperature here was 314 degrees F. So after they get all mixed, they go to a point where a little heat exchanger, we typically use a steam heat exchanger. They get heated up and then they get fed into the burner. And those things are, that having the temperature, having the fuel composition, it's actually really, really important, because off of that, then we get a pressure. So in this particular case, that RFG pressure was operating about 2.23 pounds, and the PSA pressure was 3.9 pounds. So knowing the temperature, knowing your compositions are actually key in order to understand what the fuel pressure will be at the site. As you know, I think Mark talked about it, there's a call it capacity curve, and what it is, you have on the y-axis, you have your heat release, and on the x-axis, you have your pressure. Well, one of the things, in order to create that curve for your customer, you need to understand the coefficient of discharge, which I think you guys talked about it too. And so this is the way for us to get that coefficient of discharge, by understanding what the pressure is here in Tulsa, with the temperature, with the fuel composition. So pretty cool. That's a really nice observation. But there's other data here that we also look at, right? Other than measuring fuel flow, we also measure airflow, if you will, through the burner, and that's where you see that burner pressure drop. We also measure a couple temperatures. We measure the furnace temperature, the stack temperature, and the floor, or the temperature at burner level. And those are really important when you are comparing to your customer's facility. So we understand that NOx production in this particular application is predominantly happening due to the thermal NOx, right? So the NOx being created because of the added energy of the surroundings or the energy of the combustion itself. And so matching that furnace temperature is actually very, very, very important when it comes to burner testing and when it comes to predicting emissions in the field. So if you're trying to understand what's at stake here is you have made a burner guarantee. In this particular case, I think this project had 137 burners in it. So if 137 burners get built with 137 gas tips, and they get installed in the field, and all of a sudden in the field you're not meeting the NOx emissions, and you have to go out there and figure out a solution and then do it 137 times and apply it to those burners, and that's going to be on you. So that's whenever we try to replicate, whenever we try to get as close as we can to the final product of the final process of that heater, we really do mean it. And even then, we like to work with pretty healthy margins too. So let's talk about how do we measure fuel and how do we measure air. Well, the first easiest one is going to be the pitot tube. We actually have a pitot tube right at the entry of the burner, and we use the static pressure more than the stagnation pressure of that pitot tube. We use that to get an idea of what is the pressure at the burner inlet, and then we also measure the static pressure at the floor of the heater, and essentially the difference of the two is what we know as burner pressure drop. Okay, and we use a similar concept for the measuring of the fuel flow. We just use an orifice meters, and in the orifice meter you will have a pressure transducer right before that drop, and then a pressure transmitter after it. And that difference in pressure, along with a little bit more information like temperatures, pressures, and the actual fuel composition, would actually tell you how much flow is going through that particular line. So you will have one of those guys on every single one of those lines. So that's exactly how you know the flow, the volumetric flow through every single one of the fuel lines there. Okay. The next thing is measuring temperatures. Typically, furnace temperature, floor temperature, they are most of the time measuring with what we call a velocity thermocouple. And what that is essentially the ability, so it's just essentially a K-type thermocouple, I think. And we have flue gas from the heater. It gets sucked into this particular junction thermocouple, and that's how we measure the temperature of it. The reason we do it this way as opposed to just sticking a probe inside the heater is because there's actually radiation happening. So naturally you have a flame, you're going to have a good amount of radiation going on. And so this is the best way to actually measure the flue gas temperature without having the effect of radiation. And it'll get you a little bit closer to what you see out there in the field. So pretty simple. The next measuring that gets done is flame dimension. So there are two ways to quote unquote measure flame, and this is actually a pretty wild topic every now and then. So what we do is we use what we call a CO probe, and a CO probe is just a probe that is water cooled. So it has a little water jacket that has water flowing at all times. And through the center of that probe, you actually have suction, and you actually take out a sample at a given point. So all our test furnaces are going to be equipped with ports where you stick this probe, and what you do is you place the probe in a known location and you really measure the CO at that particular location. And according to API, we define CO or the flame boundary is defined at 2,000 ppm. So if when you're measuring with CO, you measure 2,000 ppm or more, then you are in flame. If not, you're not in flame. So imagine just going through every single port. When you do it, when you're talking, you tell you're going to do a CO profile. What you're really talking about is that you're taking this probe and you're going to insert it in every single port, and then you're going to get as close as you can to, or you're going to get to the center line of the burner, and then you're going to pull back, say 6 inches, a foot, however amount you deem appropriate, and then you make that profile. Yeah.
CFD models having a good manufacturing when you're doing that?
Okay. So the question was if CFD models has any influence with the testing, and the answer is absolutely it does. Okay. So it's kind of like the CFD and the testing is sort of like what was first, the chicken or the egg, really. So we typically, when we can, we do a CFD simulation of the entire heater, okay, and we get a result. Once we do that, what we try to, if we find any issues with it, we tend to tailor gas tips geometries to get the final flame shape that we're looking for, okay? And so then what happens with that, you go to the test, you get your test done, and then you compare your CFD flame characteristics with your tested flame characteristics. And sometimes you do a little bit of tailoring on the CFD, like reaction models, for example. You do a little bit of tailoring there in order to match your testing, in order to match your burner testing characteristics, and then again you apply it to the full heater. There are instances that when you get done with that process, you find out that the end product is not what you like, and so then you use CFD to iterate on gas tips until you get what you want, and then you test that, and hopefully you're done with that circle of iteration. So it's really, they go in hand. But we definitely use both. And this is one big part to validating the CFD, because the other way to measure flame width is visually. And it's a really, in my opinion, a really poor way to do it. Sometimes you can get by it if you're not in a really constricted space, but I could probably get you guys in a room and ask you how wide is that flame, and I could get, 20 different answers. And so the visual flame width is not, the visual approximation is really not the best way to do it. It is simple though. You just show up, you just look at the thing, and you're done. That's it. That's the measurement. And it works. It definitely works for a lot of people, but not necessarily scientific, if you will. There are other things that we also get to measure in the particular in the furnace, and this is for applications like millisecond furnaces, which I think what they do is they crack hydrogen, and so essentially what they do, crack methane, and what they do here is they actually measure heat flux. They actually measure the radiating energy off of the wall behind the burner into the process tubes. And there are some heater designers that actually have a desired heat flux curve. So if you were to normalize the amount of heat being transferred off of the wall to the tubes, you'll get something that actually looks very much like that. You have like a little belly, if you will. You have a little curve. So you start at a particular location, you hit a peak, and then it just dies back down. So there are some heater manufacturers, some process engineers for the heater world that actually tailor that curve for a particular process. And so they present to us the curve that they desire, and then we get out there and make a flame shape or make a burner design that would meet that given curve. So that's a further step. That really gets specialized into a very niche application, but those are actually more common than not. We actually build one furnace 14, just for this application. So it's something that we definitely love to get after. Another pollution that we actually do record and that we actually have to that are regulated by it is noise. Burners are loud, and we typically have a threshold that we need to meet. So we use as human beings, we really cannot hear all the different frequencies. So there is an A-weighted scale that we work with called the A or dBA, and it's something that we pretty much record on every single one of our burner tests. Typically in the States, where you're looking at, it's about 85 dBA is a noise threshold. But in Europe, for example, where refineries tend to be or can be a little closer to the city, you're looking at noise threshold of like 78 dBAs. And since it is on a logarithmic scale, every time you go down about 3 dBA, you're about half as loud. So if you're looking at 78 dBA, that will be like what, 3 times as quiet? So it gets really, really complicated when you're trying to get that quiet, because you need to add more and more things to your burner to make that happen. And really the way to measure it is you just have a noise meter, and you just have to have an understanding of where the operator is going to be located. So typically it's measured about 3 foot away from the burner inlet. And again, this is set up by API. API is sort of tries to regulate this, or whatever pollution regulating body you're applying yourself to. And then finally, flue gas analysis. Measuring, this is the big deal of the burner. So here's where we measure the emissions of CO and NOx. And we also measure the oxygen, and it becomes important because you do some corrections with it. So carbon monoxide analyzer, these are actually the 3 analyzers, and I think, so this will be your NOx analyzer, CO analyzers, and O2 analyzers. They look about the same. They get calibrated every single morning, and they get maintained, I think, every 4 months or something like that. Like, that's literally what we rely on at the test center. And the CO, the way to measure CO, really what you do is you get the flue gas sample, and it's actually conditioned, so it's all dried out, and it gets through this analyzer, and you actually shoot a laser at a particular wavelength, and you actually try to measure that beam again, and you try to understand, and you understand the amount of light that was absorbed, and through that you can understand what is the CO occupancy on that flue gas. And so it'll give you a number in ppm, so it'll give you a volume number of CO of that particular flue gas. Then NOx, it does it a little bit differently. It actually does almost the opposite. So the first thing that you do on NOx, you take the NO2 and you reduce it down to NO. Once it is an NO, you react it with ozone, or O3, and out of that you will get something that is bright. Once you get that light, you can measure the intensity of that light, and then you'll have an understanding again of the volume occupancy of NOx on that flue gas sample. And then finally, O2 is measured by inducing a magnetic field. So oxygen is actually paramagnetic, and what that means is it will react with a magnetic field. And when you do that, and so you have a stream of fuel, you make a magnetic field, and that'll create a pressure difference in that flow field. If you measure the intensity of that pressure difference, then you'll have an understanding of the O2 inside that stream. And that's how we measured those particular 3 components. NOx emissions are often reported in a 3% O2 basis, right? So with that was done simply because, as you saw a second ago, you measure O2 in a volumetric manner. So back in several years ago, people figured out that, if you had high NOx, what you did is that you diluted it with more oxygen, and all of a sudden you had a lot less NOx. And that was a lie. That's not correct. So what the API has done is just essentially has you reported at a 3% O2 basis, and the math to correct the 3% is super simple. And that really is helpful, so you can compare apples to apples amongst different burner operations. So let's just go over that. Let's just see here an example where you have a NOx of 2%. You're given a particular O2, a particular ritual temperature. In this case, say your burner is operating at 25 ppm, and your client furnace temperature is 1600 degrees, and the O2 is to be corrected at 3%. And in the test furnace, you're looking at 1500 degrees of ritual temperature and about 2.5% O2, right? So really, this is all you got to do, and this is it. This is that one formula, simple formula for correcting. okay? So the first term of the right side of that equation is going to be obviously the NOx you measure in parts per million. And then all you're doing here is just a volumetric correction. You take the 3% that you corrected versus what you measure. And what that's going to tell you is going to give you the factor for the NOx that you're going to be reporting. And one big note about that is that it's not a predictive NOx. So I think in this particular case, if you take 25 ppm at 2.5% O2 and you correct it to 3% O2, you're going to get something like 25.5 ppm. That does not mean that the burner will produce 25 ppm when it's at 3% O2. This is not predictive. It's just a correction that you're applying. And finally, the temperature correction. And this one, it's a little bit more empirical. Okay, you're not correcting to the absolute temperatures. That's what's 400 degrees. It's a little bit empirical, and this is somewhat predicted. You can use that to get an idea of the NOx production at a higher bridge wall temperature. This particular correction is good when you're trying to extrapolate to about 100 degrees or 200 degrees. If you go past that, then it starts breaking down a little bit, okay? So again, if you do that, you plug in your numbers, you're going to get that the NOx reported at the customer side is going to be 23.5 ppm. It's actually super simple. So in summary, really the burner test design, it's pretty much that last safe or that last check before it gets to the field, okay? So really this is the opportunity to correct any issues that may have, and I cannot emphasize this enough when I say when you make a burner design, or really when you make any equipment design, it gets installed in the field, and in this particular application it will last there for years. I mean, I expect some of the burner designs that I've made to outlive me. So that's how long this burners get to be out there. So if you do something that is not correct, get ready to live with that for life. That's one really big thing that I want everybody to keep in mind, and that's why we take burner testing very seriously. It is not uncommon to test a burner and have a customer demonstration and something not go properly and then have that demonstration again. And it is also common for the customer say, like, I am not going to purchase a burner test. Sometimes we even do the burner test on ourselves in order to make sure that everything it's according to the spec and everything is according to what we want. It's a lot easier to fix the issue on one burner and a tiny heater in Tulsa, Oklahoma, than it is to fix it in the middle of Nebraska on 325 burners. So it's very important for you to be honest with yourself and really understand what is it that you're about to do and how can you simulate that pretty much in your backyard, if you will. And really understand what you're measuring. Okay, the fact that you get a temperature that says 1500 degrees doesn't mean that you have matched everything. You got to understand where does that leave in the final process and what does that really mean. And finally, on NOx emission measurements, we understand how we take them and we understand that we can correct for that. Please understand that the O2 correction is not predictive. Okay, it's just a correction factor for dilution. And finally, there are other units of NOx, like pounds per million is one of them that you could report into. And guys, I think that's about it. Does anybody have any questions? We have a question in here.
How long does a burner typically stay in testing before it's released to the field? Like, even if everything goes right, is it like dependent on like if there's new technology like with it versus like a burner similar to something that's made before?
Yeah. So you call it right, like right. What you said there at the last sentence. So the question was, how long does a burner test last, right? And so I think she made a really nice line at the end. It's like, okay, well, does it matter if it's new technology or if it's older technology? So that really is a huge driver, right? When it's a burner that we have tested literally hundreds of times, then the duration of the burner test is not as long. Right? I think a typical duration is going to be about a week. But whenever you have a newer technology, then that gets a little longer. I mean, a burner test can be a couple weeks, if you will, 2-3 weeks. And the big driving factor is the number of operating parameters that you have, the number of different test fuels that you have, and even the number of burner sizes that you have. One heater can have different burner technologies in it. So those are the main drivers for those. So I would say anywhere from 1 week to 3 weeks is about the testing time that you go in one particular project. Is there, yeah?
How much would a burning test cost in relation to the cost of the actual burner?
Okay. So a burner test, so a really simple, short burner test can cost you anywhere from 25 to 35 grand. Okay. One burner can cost, I don't know, 5 to 15 grand depending on the burner type. So if you were to purchase only one burner, your test would actually cost more than the burner itself. And that actually has happened. Okay, so there's been some projects where you have a heater that only has one burner, but they still purchase a burner test because it's required. But there are other more intensive tests. For example, a test like the one that we just saw, that's like a $150,000 test for a heater that's going to have the burners. So it really depends the number of burners and then the complexity of the test itself. Fair question. Are there any questions online? I think we're good. I see somebody nodding their heads. All right, guys. Well, if there's any questions, thank you so much.
I'd like to add something to